We're going to revisit now a case that was familiar in one dimension, one which we have an acceleration, but it's a constant. In one dimension, the equations of motion were that the position y would equal some initial value plus an initial velocity times time plus a 1/2 a times the acceleration times time squared. I am writing all of this with little subscripts, so this is y, y naught. Notice I'm writing a vy naught and ay. That's because I'm going to talk about two dimensions here momentarily. But in the other equation we had to remember here is that this velocity in the y direction under uniform acceleration or constant acceleration would grow or decrease linearly with time depending on the sign of that acceleration. If the sign of this acceleration was positive, then the speed vy would continue to increase linearly with time. If the sign of this acceleration was negative, it would decrease linearly with time. In two dimensions, we actually have two components for the velocity, and likewise we have two components for the position. So our equations of motion are v of t is equal to v naught plus a times t, and r of t is equal to r naught plus v naught t. That's 1/2 a t squared, where v, v naught, and a, and r are all vectors. That means that they have a component in the x direction and a component in the y direction. We want to consider a case where the acceleration is a constant. In particular, we're going to be interested in the case of motion in 3 dimensions where we know that gravity points straight down, so that the acceleration vector is 0 in the x direction, minus g in the y direction, and 0 in the z direction. If z is pointing out of the page, x is along the horizontal, and y is on the vertical. In this sense, we expect that dx will be a constant, and vy is constant. Excuse me, vz is constant. Vy should be changing all the time, because only Vy has an acceleration Ay when we have gravity in the y direction. Let's consider what this means in a little bit more detail. Imagine I roll a ball along the floor. There's no gravity there, and it's a one-dimensional problem. Let's suppose I roll it along the floor with a horizontal component of velocity of 10 meters per second. I can imagine what the equation of motion is. It's just that x linearly grows with time and the velocity is constant. So at time t equals 0 seconds, position is 0 meters, velocity is 10 meters per second. At 1 second, x is now 10 meters larger, velocity is still 10 meters per second. At 2 seconds, the velocity is still 10 meters per second because it's a constant velocity. I'm just rolling it along the floor. but the position is 10 meters more. It's now at 20 meters. At 3 seconds, I'm up to 30 meters, and it's still moving at 10 meters per second. It's just marching along the floor. That's very different from what we developed when we said that we drop a ball. Let's suppose we dropped a ball from the top of a building. Since little g is approximately 10 meters per second squared, then at 0 seconds I might be at 0 speed because I've just dropped it and I've advanced 0 meters. But at 1 second, my equations of motion, the velocity grows linear with time by the acceleration, now says that the velocity will be 10 meters per second. Remember that Vy is V naught plus AYT. And AY is this constant G. And Y is going to equal Y naught plus V naught YT plus 1/2 AYT squared. So at 1 second, these two terms are 0 in the way I'm setting up this problem because I'm dropping the ball from rest. So it's just this last term that starts building up. At 1 second, 1/2 times 10 for the acceleration times t squared, which is 1, gives me 5 meters. At 2 seconds, I get 20 meters. And the velocity has grown to be 30 meters per second. Excuse me, 20 meters per second. And so on. So the position is just advancing along, and it's not advancing uniformly, it's growing quadratically because of this t squared. That's if I just drop a ball off of a building. But now let's imagine a more complicated problem. Let's imagine I fling a ball off of a building. I throw it straight out ahead of me, like a baseball. Well, I have to analyze its motion in two completely separate coordinates because they are acting independently. In the x direction, if I'm just throwing the ball forward, it continues to just march along like this. Same speed as always in the horizontal because it's whatever I threw it out across the plaza with. But in the vertical direction, if I was throwing it straight out, it was initially moving at 0 speed. So now it's acting like a ball that's dropped, and it's starting to accelerate. Well, the actual motion is the sum of these two components. So displacement is a vector, and if it has an x component and a y component, then the net displacement is to be down here. And the net velocity is the sum of this vector right there plus that little vector right there. And so it's moved like so. After 2 seconds, it's just marched along in the horizontal, but it's now dropped further in the vertical. And I have to take that as my x projection, and that is my y projection. The sum of those two vectors looks like that. And I keep doing this all the way through. It continues to march along in the x direction, but it's dropping in the vertical direction. And after several more seconds, it's over here. It's still just marching along in the x direction, but it's dropping faster and faster in the vertical direction. And after even more time, it looks like it lands. In the x direction, it would just keep on moving, but in the y direction, it's found the floor. So each of these increments is really the sum of two vectors. There's a delta x and there's a delta y. And there's a delta x. And there's a delta y. Notice that delta x is always the same. It's delta y that's growing. In the same way, the velocity in the, well, for a really reason, the velocity in the horizontal direction is always the same. It's the velocity in the horizontal, in the vertical, that's always changing. So as we move further into problems with projectiles moving through two-dimensional space, we have to get good at the idea that these two motions in the horizontal and the vertical direction are completely independent. And that's because of our original equations here. That these equations separate out as vectors. That there's an x component of velocity that depends on the initial x velocity plus the acceleration in the x direction times time, and the position r of t has an x component that depends on the initial x and the initial velocity in the x direction times t times the acceleration in the x direction times t squared, and so on. And this whole thing repeats for the y direction. In the y direction, the acceleration in the y direction might be different than it is in the x direction. And the y initial velocity might be different than the x initial velocity, and so on. So we'll have a complete set of equations like this one, or this pair, one for the x direction, one for the y direction, one for the z direction, where we'll have to fill in what these constants are, and then let the clock run forward.